Okay, so we have 40 minutes to cover 3 book sections making up an entire chapter. And we can totally do it. Chapter 4 is a lot of stuff that's very analogous in many ways to single variable optimization. So a lot of this is going to seem really familiar. And also the methods that you're going to use to solve problems, where the rubber meets the road, it's very mechanical. It's very follow the process. Okay, so here we go. So I should point out, so a lot of this stuff is stuff you're going to read in the book, right? I mean, so do make sure to read through the book. Again, I think you'll find a lot of it looks very familiar, and I think it's very readable. Okay, I want to comment first about Taylor polynomials. I'm sure y'all remember this expression right here from single variable calculus classes. Taylor polynomials are good for a lot of different things. Where does it come from, right? Why do we talk about, how do we even define Taylor polynomials? And there's different takes. I like to think of it as the unique polynomial of a certain degree that mimics the function you're interested in as much as is possible, and specifically what I mean by that is it has the same value as the function you're interested in, the same derivative, the same second, third, fourth derivative, etc., all the way up through and including the same kth order derivative of the function you're interested in at the point in question, at the point A, of course. All right. Okay, so yeah, what I like about this point of view is it's a pretty simple point of view. It's telling you what the purpose of the Taylor polynomial is, and all of this algebra down here is just making precise what we mean by that. Okay, so in a multivariable situation, by the way, this does have to be real valued. We're not going to consider vector valued, and not that different, but it's not, we don't need to go beyond real valued. When you have multiple input variables, we basically aim for the same goal. We're looking to find a polynomial of the appropriate degree that mimics whatever multivariable function we're interested in. And again, we mean the same thing by that. We want it to have the same value as the function we're interested in. The same, how to say this? First derivatives, plural. Keep in mind, if you're doing single variable, there is only one derivative. But if you're doing multivariable, there's several different partial derivatives. If P is going to mimic F, it had better have all of the same partial derivatives as F. And then likewise, second, third, and fourth, and higher partials, all the way up to and including the kth order. And again, keep in mind there's a bunch of them, right? There's a bunch of mixed and unmixed different higher order partials, and all of them have to agree with the function that we're interested in. So I think it's a pretty good pitch that if a function can actually do all of this, then it's a pretty good approximation of the function f, and very strongly in analogy with single variable Taylor polynomials. All right, so when k equals 2, and this is all we're going to write down. The book has the general formula. We're not going to have any need for that, but it's just more to write down. It's a little clunkier, not going to be something we'll need. The second degree Taylor polynomial for an appropriately regular function of several variables is this right here. So this is just the answer. This is the thing that makes it work. You'll probably see some of this coming. I mean, after all, this is the linear approximation, right? So kind of stands to reason those would be the first 2 terms here. And the last term is a little harder to see coming. This is what it ends up being. It's this expression right here. This thing called HF is it's called the Hessian matrix. It's the matrix of second order partials, and arranged in the obvious natural way. And plug into this expression here, and that gives you your second order term, and that's your second degree Taylor polynomial for a given function. Yeah.
So we're only going to go up to second degree?
Yeah, that's right. We're not going to have any need to go higher than second degree. Right. Okay, so plug and chug. Y'all can y'all can multiply. All right, so I'm going to let y'all mostly do the rest. I will point out one thing for your consideration. You'll notice this is a little bit more complicated of a second order term than we saw in the single variable case. This is not just, second derivative, times something squared. Right? This is has a matrix vector product in it. This has a dot product in it. So it's a little weird. In fact, you'll also probably recognize this as being something that y'all have studied in a linear algebra class. This is called a quadratic form. Right? So literally, if you want to understand second order Taylor polynomials, you need to understand quadratic forms. And here's the good news. We're not going to be doing terribly much with what y'all learned about quadratic forms in your linear algebra classes. We're not going to need very much of that. Okay. All right. So there you go. That is section 4.1. 1 down, 2 to go. Okay, so extrema of functions, optimizing functions, you can say it in different ways. I just want to remind you very quickly from single variable calculus, and I'm not going to go through all the details on the page here. Hopefully, presumably, y'all remember most, anyway, of this stuff from single variable calculus. The big picture point that I want to make sure everybody understands is that when you're doing optimization, you're not really finding extrema. What you're actually doing is eliminating candidates until only a handful remain, and then you're just going to kind of plug in and just look and see what's going on, right? So the active mathematical computations that you do don't find anything. They just show where we can't draw any conclusions. So specifically, these 3 conditions allow you to conclude the function is in the process of increasing, and if the function is increasing, there's no way that it could possibly be a maximizer. So let's look, for example, at this point right here. Right, at this point, presumably the function's differentiable here. Let's just take the cue from the picture. The derivative is clearly not 0. This point is in the interior. It's not one of the boundary points. This function is literally in the process of increasing. There's no way in the world that this could possibly be our maximum. Functions still get bigger, right? Likewise, this point over here. Now, that point is not increasing as you go to the right, but as you go to the left, the function is getting bigger. So again, can't be the maximizer that we're looking for. So the good news is this little elimination argument actually eliminates almost all of the points, right? And this is deductive, right? This is for sure, guaranteed. None of these points. Let's see, wait a second. I missed. Sorry, let's try that again. None of these points I'm highlighting in red could possibly be the maximizer we're looking for. The only points that have any chance at all of being the maximizer we're looking for are points that don't get eliminated, points where one of these conditions fails, and therefore I can't make the argument in the first place. These are what it looks like when one of those conditions fails. There's the boundary points. There's this point where the function fails to be differentiable. There's this point and this point where the derivative fails to be non-zero. In other words, the derivative is 0. Right? So these green points, these very, very few, hopefully, presumably, fingers crossed, very few remaining points that aren't eliminated. What do I actually know about those points? All I know is that my argument fails. I don't really know anything else. Basically, all I know is that I don't understand what's going on at those points, right? And I think this is a big underappreciated fact about how optimization works. So we call them critical points. This is just a confession. Yeah, I have no idea what's going on there, right? And these are the points that we're just going to have to check out kind of by hand afterwards and just be like, let's plug in and see what the value of the function is at those 5 green points. That the maximizer, if there is one, has got to be one of those. Everybody on board? It all kind of sound familiar? Notice, not only are these 5 points not all maxes, they're also not all maxes or mins, right? There's some that are neither max nor min. Well, in particular, the middle one, it's not a max or a min. This is why I say when you find critical points, you don't know what is going on at those points. Okay, all right. Now with that all settled, let's talk about the multivariable version of this. It's really analogous. There's a set of conditions I can write down that guarantees that the function is increasing in some direction at least, which means that couldn't possibly be the maximizer we're looking for. The function's still getting bigger. And so a great example on this little picture I have is that point right there. This little point right here is in the interior of our domain. Taking the cue from how it's drawn, we're going to go with the interpretation the function's differentiable there. And this function seems to be kind of increasing as you kind of go into the page, maybe about like that. So the gradient vector is not 0. This couldn't possibly be a maximum. The function is in the process of still getting bigger as you go in some direction in the domain. Can't be a maximizer. And again, this eliminates almost every point in the domain. Vast majority of cases, right? The only things that remain are where, whoops, I'm going to get to the highlighter. Sorry, my bad. The only points that remain are points where at least one of those conditions fails. Therefore, I can't eliminate it. And this is what those look like. Either x is not in the interior, therefore it's on the boundary. The function is not differentiable, or the gradient is not non-zero, aka it's 0. And so just like we did in single variable, we're going to call these critical points. There are very few of them. Looking at the picture we have here, let's see here. Well, there is the whole boundary. Yeah, that's a lot of them. It's something we're going to have to deal with. We're going to have to figure out how to... there's infinitely many points on the boundary. Right? We're going to need... We can't check all of them. We don't have that kind of time. So we're going to have to figure out some method for how to deal with the boundary, and that's going to be coming in the next section. So we're going to momentarily punt on that. But here, the gradient is 0, taking the cue from the picture. Here, the function fails to be differentiable. Here, the gradient is 0. Here, the gradient is 0. So other than boundary points, these are the only candidates that could possibly be the maximizer we're looking for. Okay. All right, now what does that mean about these points? Are they maxes? No. Obviously not. Look at this one. Right? That's not a max. Is it a min? Nope. Right, so again, just because you found something as a critical, that doesn't mean that you know anything about it. In fact, it kind of means specifically that you don't know anything about that point. And the bad news is that in multivariable, even when you have as small as a 2-dimensional domain, there's just a lot more room for functions to kind of move around and be weird in different directions, and all sorts of strange things can happen. This thing right here, called a saddle point, giving an indication, I think, that terminology was chosen before Pringles went into business. Right? This should be called a Pringle point, right? Am I wrong? Of course it should be. Points like that are not analogous to anything in single variable. There is no single variable analog of that. Right? And it gets weirder than that. If you look at, whoops, where'd it go? Here it is. This picture right here. Right? This is a pretty good 3D image somebody created with a computer, and you can see it's kind of vaguely Pringle-like, but it kind of goes up, down, and down. It has kind of 3 ups and 3 downs. And they call this a monkey saddle because it gives a downward sloping place for his 2 legs and also the tail, which I find hilarious, right? By the way, I have discovered when you do a Google image search for monkey saddle, scroll down far enough, you will see somebody has actually put a monkey on a saddle on a dog, right? And scroll down and find it. It's pretty funny. Okay. So, and by the way, it gets weirder than that. If you ask, is this the only kind of sort of new weird possibility? Just Pringles and monkey saddles? Not at all. In fact, let's see if we can find one here. My favorite next example is, I have to click image, is a spider saddle. Oh, here's a pretty good one. See this picture right here? Let me go ahead and click on that. Oh, that doesn't help much. Anyway, you can see up, down, up, down, up, down, up, down, up, down, up, down. There's endless different kinds of weirdness that can happen, right? And that's just because we have different directions that the function can do different weird things in. Again, there is no version of that in single variable. Okay. Alrighty, let's do one. Let's find all the critical points of this function. Now, reminder, we have a very specific definition of a critical point. A critical point is a point where any one of these conditions happen. Notice these are ORs, so any one of these conditions qualifies a point as a critical point. Notice that means that you have to check all of the conditions, because there will be some points that satisfy one but not the other 2, or maybe they won't satisfy the first 2 but they will the last one, etc. So you got to check all the conditions because any one of them would make something a critical point. Okay, so here we go. This function is defined on all of R2. There's no values of x and y that create a problem. R2 doesn't have a boundary. Never ends. So there is no boundary critical points. And we have done our duty on point number 1 there. Okay, next. Is it differentiable? Well, yeah, of course. It's a polynomial. All polynomials are differentiable. So there are no differentiability critical points. There are no points where differentiability fails. All right, so again, we've done our duty. Lastly, where is the gradient equal to 0? Right? Well, take the gradient, set it equal to 0, and solve for x and y. And again, this is just a very plug and chug thing. Notice this first equation means x is going to have to be plus or minus 1. Notice the second equation tells me that y is going to have to be 0. And there's really only 2 points that can do that, and those are these 2 points right here. So we've just found all the critical points of that function. Everybody see what I'm talking about here? See, that's very plug and chug. It's very quick. Okay, common mistake that I see students make very regularly. Students reason as follows. I'm subconsciously, perhaps, right? Not explicitly. They think, you know what? This is the one that gives me the most critical points. So this is the only one I have to do because the maximizer that we're looking for is probably one of these. Right? Well, now that implicitly kind of hangs on the assumption that all we're interested in is the final answer. And that's, again, just not true. It's not what we do here, right? In this class, we're interested in reasoning, not, the number in a box at the bottom of a page. Right? So you got to check all the conditions, right? You have to check all 3 of these because all 3 of these will give rise, sometimes anyway, to critical points. And so if as we are interested in valid mathematical reasoning, you got to give me all of the valid mathematical reasoning. So I hope that makes sense. You can take there's different points of view on this point. You can take this as Okay, so I've got to do this little silly business right here, or I'm going to lose points. This is the wrong angle on this. Think of this as, hey, all I have to do is some really easy little silly business, and I get points. That's the way to think about this. Does everybody see my angle on that? Okay. So please make a point, no pun intended, to check all three of the conditions. Easy money. Okay, yep.
How do you know that every point is interior just because it's defined in R2?
Yeah, because I suppose if I had written this question a little bit more carefully, I would have written the function f defined, for R2 to R1, and this function is defined everywhere on R2. So the unwritten but implicit domain for this function is all of R2, and R2 just doesn't have a boundary. So yeah.
Thank you.
Yeah, sure. On an exam, you're very welcome to ask that question, and I'll be happy to clarify. Yeah. Okay. Also, on an exam, I would probably have been more careful about how I wrote the question. Okay, now there is something about this example that is a little unrepresentative, and that is the algebra worked out really, really easily, right? In particular, solving this vector equation, or you might say solving this system of equations, by the way, nonlinear system of equations, and this is sometimes really, really hard. This one happened to be really, really easy. I just want to show you what solving a nonlinear system of equations can look like in some cases. And here's one, right? Nonlinear system of equations. Something like this you might encounter in trying to find critical points. Well, this first equation tells you that x squared is y squared. And here's where a lot of students mess up. A lot of students will say, oh, well, that implies that x must equal y. And that is not true. Straight up doesn't. Right? Now, why do students draw this conclusion? Is it because they don't know how squares work? No, of course not. No, students do this, I'm convinced, because their high schools have told them to do this and told, don't worry about the minuses. I've seen stuff like that, when I was in high school. This is terrible advice, and you got to try to erase that. If you have a experience in your past, kind of like I had when I was in high school, please make sure not to retain that point of view. You cannot just do illegal algebra because it's convenient. It just doesn't work. All you can conclude from this is that x is equal to either y or minus y. Either one. Could be either. I don't know which. Is that cool? Everybody's happy with that? And you got to check both cases. So, for example, let's start with this first case here. If x is equal to y, well, you can take this, plug it into that equation, it becomes that, and you can solve for y. No problem. And of course, keeping in mind that this is in consideration of the case where x equals y, you can solve for x, and that gives you 2 critical points. And again, a lot of students would stop here and declare victory and move on to the next question, and here's what they've missed. The students that don't consider the second case, right? You got to consider the possibility x could be negative y. It totally could. And if it does, right, notice that gives you a different equation to solve for y. You will find a different y in particular. And now again, once you know y, that allows you to conclude your critical points. And one of them happens to be a duplication, right? We already had that one. So, no news on that. But notice we definitely get another critical point that was not on our previous list. So if you're sloppy with your algebra, you will miss critical points, and that's why it's not okay. Does that make sense to everybody? All right. Okay, moving along. Second derivative test. Y'all will recall the single variable second derivative test. I'm going to give you a take on that. My point of view on the second derivative test in single variable is that, well, if you're looking at a point where the derivative is 0, this term goes away, and all we need to know is whether this term is always positive or always negative. 1/2 is always positive. A square is always positive, or 0, but never negative. And so whether this term is always positive or always negative boils down to whether this single factor, the second derivative, is always is positive or negative. Right? And so that's why the second derivative test in single variable is as easy as it is. You just have to look at that second derivative, and positive tells you something, negative tells you something, and you infer accordingly. Okay, so we would like to do something similar for multivariable. Again, if the gradient is 0, this whole term goes away. And all we have to do is understand this term, and here's where things get weirder. That term is a quadratic form. It is not as simple as just look at one thing. It's either always positive or always negative. It's just not, right? Quadratic forms are complicated. Linear algebra, like Math218, Math221, whichever you took, you saw how quadratic forms can take various different behaviors. And in particular, there is this thing called positive definite. There is this thing called negative definite. And sure, positive definite means you have a min, negative definite means you have a max. Yeah, fine, right, totally. But there is also the possibility of indefinite. And indefinite means you're going to have a saddle point of some sort. I don't know if it's a monkey saddle or a spider saddle or maybe just a Pringle, right? Who knows? Or maybe something weirder. I like to point out there's something I would call a shoulder point. Like imagine, like right here, this point on my shoulder, right? It's kind of level there. Gradient's equal to 0. Maybe that's a critical point. It's kind of a local max in the forward-back direction, but it's an inflection point in this other direction. Right? All kinds of weird nonsense that can happen. Okay. So how do you decide? We're going to take advantage of the fact that that Hessian matrices are symmetric. They're symmetric because partial derivatives don't depend on which one you do first, right? Assuming the function's appropriately nice, which we're assuming. So symmetric matrices have some really nice linear algebra properties, flashbacks to your linear algebra classes. Symmetric matrices are diagonalizable. You also know cool things about their eigenvalues and there's a lot you can do, right? Just knowing the matrix is symmetric. And that allows you to streamline very nicely the matter of deciding if it's positive definite or negative definite. In fact, let's just cut to, is it a local max or a local min? It is different, as you can see, very different from the single variable second derivative test. We have to look at the determinant of that Hessian matrix. Right? And it breaks down by a pretty simple little flow chart. If the determinant's positive, then you have a fairly familiar looking second derivative test that you can just plug right into. If the determinant is negative, you get a saddle point. End of story. Just a saddle point, right? If negative Hessian determinant means saddle point. And of course, it's also possible the test that the determinant will give you 0, in which case the test fails. And just keep in mind, test fails means we draw no conclusion. It does not mean that it's not a max. It does not mean that it's not a min. It means we know nothing. We conclude nothing. All right. Okay, so The example that I have here is very mechanical. Y'all can totally read it. Time being an issue as it is, it's not going to be a good choice for us to go through this. By the way, one thing to keep in mind, you can always click through my YouTube channel in previous semesters and find previous semesters where maybe I did talk about this. Right? And so if you want to see the details, go ahead. You can just look back to, I don't know, I don't keep track of what I do when, right? But I'm sure there is an old term where I did cover this. Okay. This next business about global extrema, you're not responsible for. It's a luxury that I like to be able to do when time permits. It's pretty low priority, though. What we do need to get to is section 4.3 on Lagrange multipliers. Good news, this is also very mechanical. So what I'm going to do here is I'm just going to give you some very broad strokes on what kinds of questions does this address, roughly why does it work, and then let's start seeing some examples. Okay, so the kinds of questions we're interested in. You want to optimize a function with a constraint. So for example, look at this example right here. We want to optimize distance to the origin. Right? Distance to the origin is a function. That's what we want to optimize. But we have a constraint because I'm not going to consider all possible points. Right? Obviously, the origin is the point closest to the origin, right? But that isn't the question. The question is, among these points, among points that satisfy this equation, not including the origin, you'll notice, among these, which one is closest to the origin? Actually, a really hard problem. Okay. All right. So in any of these kinds of constrained optimization problems, there's some function you want to optimize, and there is some function that describes your constraint, and there's a very specific angle that we're going to take on this. The function, one of whose level sets gives you your constraint. That's what we're going to call the constraint function. Okay, so all of this works by way of level sets describing our constraint. You got to make sure to interpret the constraint function by that connection. All right. So a couple of easy examples of this. If you want to find the box of greatest volume that you can make with a certain amount of area, maybe you have a limited amount of cardboard or something like that. Well, what you want to maximize is volume, and your constraint is that you're looking for a fixed amount, right? Level set, fixed amount of area. So there's your objective function and your constraint function. Okay. All right. All right. How are we going to do this? Good news, there's another elimination argument. Good news, the elimination argument works practically everywhere. All we're going to have to do is look at where that fails. So here is how the elimination argument works. 3 conditions. If these 3 conditions happen, then you've got a picture basically like this. Keep in mind that gradients are always perpendicular to level sets. Right, so that's a key fact. That's why Lagrange multipliers comes from the point of view of level sets. And with that noted, all we got to do, if we want to find critical points, is just look where these conditions fail. So where the one or the other of these functions fails to be differentiable, or where the constraint gradient fails to be non-zero, or where this little inequality fails, in other words, where you get an equality. So you've got these 3 conditions here, and if any of those happens, we've got a critical point. So it's just a matter of, again, you got to check all 3. Can't emphasize that enough. This is good news, not bad news. This means easy money. Take the easy money, right? But you do have to check all three conditions, and that'll find your critical points. So let's see how the algebra works on one of these. Now again, I'm going to kind of hit the highlights. Here's our two functions that we're interested in here. Notice they're both differentiable. Boom, I just scored 1, maybe 2 points, possibly 3, depending on how the rest of the question goes. Easy money. Take your free points, right? Okay, but you do have to do that. Second, we look for where the constraint gradient is 0. Here's the constraint gradient. Here I've rewritten it using matrix algebra. And if I want to know where that is equal to 0, we flash back to our linear algebra class. I hope y'all are good with non-singular matrices. It really comes up a lot. I am going to assume that you're good to go on non-singular matrices, and this is non-singular because the determinant's not 0. That means the origin's the only solution, and it's tempting to call this a critical point, but it doesn't satisfy that equation, so it can't be a critical point. It was never a candidate in the first place. Right? Does that make sense? If I'm trying to figure out who's the tallest person in this room, right? And if I've got some fancy method to eliminate candidates, and it turns out my answer is Michael Jordan. Yeah, no, he's not a candidate. We're looking for the tallest person in this room specifically, right? So don't indicate something as a critical point that isn't even a candidate in the first place. Okay. All right. Lastly, we write down what I like to call the Lagrange condition. This is the equation that's the most, I guess, significant new equation in this method of Lagrange multipliers. And you write that all down. You got your gradients, right? The gradient of f is this. The gradient of g is this. Having one be a multiple of the other just means that. And along with your original constraint, you now have 4 equations and 4 unknowns to solve. And here's where we enter into, how do you do this kind of algebra? And there's a couple of sticky wickets that you got to be aware of. I'm going to show you just the sticky wickets. Again, y'all can read through the rest of the algebra. Lots of students will make the mistake of writing this down first. Cancel the lambda, no sweat, and then boom, you got these 2 equations, which you'll notice allows you to write some relationships between x, y, and z, and really nice progress to be able to write down relationships like this. The trouble is, not fair. You can't cancel the lambdas. You can't cancel something that might be 0. Right? Easy example. Here's a true statement. I can't just cancel the 0. That would say 0 equals 8. That's nonsense. Right? This is a real problem. Real problem. High schools don't spend enough time, in my opinion, warning students about these very serious problems that will lead you to garbage. Right? So we've got to eliminate the possibility that lambda could be 0. And all you got to do, good news, very often, look at something like this, and it'll give you what you want. Right? Lambda couldn't possibly be 0. If it were, this equation couldn't possibly work. So now again, easy money. Right? All you got to do is make that little quick little deduction, right? Doff the cap to the possibility of making sure that you're doing legal algebra, and then again, that'll be that's worth points, right? And then you can do that algebra. And by the way, at this point, it's all over but the shouting, because once you know these relationships, then this equation allows you to solve for z. And once you know z, That allows you to find your critical points. Everybody see how that works? Okay. So again, I'm afraid I didn't quite make it. So I'll remind you, if you want to see these last two examples, and they are good ones, I especially want to draw your attention to the last example here. Go to a previous semester. There will be a past semester somewhere back there where I talked about this at length. See y'all later. I enjoyed working with you this semester. See you on Friday. Good luck on the test. Hang on just one second. Oh, and don't forget about attendance if you came in late.